Hello, Math 3. Welcome to Lesson 6.2. Again, this is review material. You should be able to do most, if not all of it on your own. So go ahead and try graphing all of the warm-up problems. So pause the video, give them a try, and then come back and check your answers. Okay, now that you have tried all the graphs, I'll go ahead and walk you through them. All right, so our first graph here, this is the parent for a linear function, y equals x. So that's going to go through the origin and have a slope of 1. Okay, so it's going to look something like that. Okay. Now, at the end, if you looked ahead, after you graphed all these, you were asked to identify domain, range, max, mins, in behaviors, etc., and so forth. So let's just go through that real quick. On our linear function here, you could see domain is all reals. Range, also all reals. We don't have any max or mins. In behavior, as x goes infinity to infinity, the function goes to infinity. As x goes to negative infinity, the function goes to negative infinity. We do have a 0 right there at the origin. It's increasing over all real numbers. Let's see, no asymptotes, no symmetries. Well, I guess it is symmetric with the line y equals x. And it has a slope of 1, intercept of 0. So there you are. There's your parent for linear. All right, next graph. This is our basic exponential with the base of 2. So we go ahead and graph that. Remember 2 to the 0 power is actually 1. Right? So there's your y-intercept. 2 to the first is 2. 2 cubed is 8. Okay. And then 2 to the negative 1. Remember that means reciprocal. So that's a half and then a quarter, so on and so forth. Okay. So there's our graph of y equals 2 to the x, our parent function for exponentials. All right, domain here, all reals, range. Notice the range isn't all reals. We never go below the x-axis on this function. So our range is from 0 to infinity. Okay, and that's an open boundary because it never actually touches 0 because that is a horizontal asymptote. So we have an asymptote of y equals 0. And since we never actually hit that x-axis, we don't have any roots. There's actually no zeros for this function. Let's see, in behavior, as x goes to infinity, the function goes to infinity. As x goes to negative infinity, the function heads to 0. That's why we have our horizontal asymptote. No max, no mins, and it is always increasing. So it's increasing for all real numbers. Okay, moving on. Our next graph is our quadratic, and the simplest quadratic, y equals x squared. Okay, that's going to have a vertex at the origin. And 1 squared is, of course, 1. Negative 1 squared, also 1. 2 squared is 4. Negative 2 squared is 4. 3 squared is 9, and negative 3 squared also 9. So we get a nice parabola. Okay, so there's our parent for our quadratic. All right, domain, all reals, range. Notice, again, we do not cover everything vertically, right? We have a minimum here. So our range is from 0 to infinity with 0 included. So this is a closed boundary or a bracket in our interval notation. Okay, we do have a 0 right there at the origin. We don't have any asymptotes. We do have a minimum right here at the origin. That is a relative as well as an absolute minimum right there. Okay. Our intervals of increase and decrease. You could see we are decreasing from negative infinity to 0, and we are increasing from 0 to infinity. Okay, so moving on, our next type of graph is an absolute value graph. So with an absolute value graph, we have a vertex, and again, the parent, the vertex is at the origin. And we have a slope of +1 when we go to the right of the origin, and we have a slope of -1 when we go to the left. Okay, so there's our parent graph for our absolute value. Domain, all reals, range. Again, notice we never go below that x-axis, but we do touch it. We do have a 0 there, so 0 to infinity with 0 being included. We do have a 0 right there at the origin. We don't have any asymptotes. We do have an absolute as well as relative min right there again at the origin. We are decreasing from negative infinity to 0, and we are increasing from 0 to infinity. And we do, oh, I forgot on the last graph, we do have symmetry, right? We have symmetry over the y-axis. Same thing back here, jumping back to our parabola, we had symmetry over the y-axis there. Okay, moving on. Our next graph is our parent graph for a step function. Okay, so when we put in 0, we get 0. Now, we're going to keep rounding down, right? Keep rounding down. That's what those symbols mean until we hit 1. So at 1, we'll jump up to 1. But all of these fractional values here, we were rounding down and then an open circle. This is really small, hard to see, but there's our step function. Okay, and it keeps going, right? Okay, so domain, all reals. Range is interesting. Okay, notice our range. Yeah, we're going down forever, we're going up forever, but we're not hitting those fractional y values. So our range is simply all integers. And yes, we do have zeros. Our zeros are all right there. Okay, from 0 to 1, but 0 is included and 1 is excluded. So our zeros from 0 to 1, like that. We don't have any asymptotes. No absolute or relative max or min. Well, no absolute max or min. As far as relative, obviously each step has a relative. Let's see, in behavior as x goes to infinity, the function goes to infinity. As x goes to negative infinity, function goes to negative infinity. Okay, moving on. Our next one, this is a polynomial. It really isn't the parent. We don't necessarily have a parent for polynomial functions, but this is just kind of a general polynomial function just to test to see if you could graph that successfully. All right, so hopefully you recall, find your zeros, right? Here's my factor. If my factor is x minus 4, my 0 would occur when x is positive 4. Okay. Next factor is x plus 2. So that means my 0 will occur at negative 2. Final factor, x minus 5. So that 0 will occur at positive 5. Okay. Now, the 4 is a single root, negative 2 is a double root, and 5 is a triple root. Our a value is positive, and the total degree here is 6. That means both ends will go in the same direction, and with the positive a, that direction will be up. If you really want to, you could find your y-intercept. That might be a good plan. Finding my y-intercept, I would have, let's see, put 0, put 0, put 0. I actually have a really large number there. So we would be doing negative 4 times negative 125. That's a big number. So I'm going to cross off the values on the y-axis because my y-intercept is way off my paper if I follow their scale. So let's just ignore their scale, okay? All right, so negative 2 is a double root. That means we're going to come down here. We're going to bounce off of our double root just like a quadratic because it's a root of 2, double root. Okay, then we're going to come up, and again, our actual intercept is really high, but let's just pretend that somewhere up in here, is whatever that 16 times 125 is. Okay, then we're going to come back down. We're going to hit our next root, which is 4, and that's a single root, so that means we're going to pass straight through it. We're going to go down, and then at some point we're going to turn back around and have a triple root, so we're going to kind of flatten out there a bit and then proceed. Okay, so that's the best I can do on that graph with this graph scaling. If you really cared about finding this absolute minimum over here, you could look into that a little bit more, but all we want you to do is be able to say there's an absolute minimum. Over here we have a relative minimum. Over here we have a relative max. There is no absolute max because our end behavior goes to infinity. Okay, so domain, all reals, range, from whatever this value is right here to infinity. I'm not going to get into that. You'll learn how to find that when you do calculus using derivatives. We do have some zeros though, and that's one of the things we did focus on here, right? Our zeros are at negative 2, positive 4, and 5. Negative 2 is a double, right, or multiplicity 2. 4 is a single, or multiplicity 1. And 5 is a triple root, or multiplicity of 3. Okay, let's see, we don't have any symmetries here. We don't have any asymptotes here either. And if you want to go over intervals of increase and decrease, you would have to, again, find this point and find this point to get those intervals accurate. But we're basically decreasing to here, increasing to here, decreasing to here, and increasing. Okay, moving on. Our next function, parent for rational. Okay. Notice here with rational, when we have a value in the denominator that's a variable, we're going to encounter asymptotes and or holes. In this case, we have an asymptote. Our asymptote is at x equals 0. Okay, so vertical asymptote right there. All right, moving to the right and left of that, we get a value of 1, 1. When x is 2, we're at a half. When x is at a half, we're at 2, so on and so forth. So the right side of our graph looks something like that. And then the left side looks something like that. And there we go. There's our parent for rational functions. Our domain, all reals except 0. Right? You could write that in interval notation if you prefer. Range is the same deal. All reals except 0. Okay. Notice, because we never hit the x-axis, we don't have any zeros. But we do have asymptotes here, right? We have our vertical asymptote at x equals 0. We also have a horizontal asymptote at y equals 0. Okay. No absolute max, no absolute min, right? Because our end behavior. As x goes to infinity, we approach 0. But as x approaches 0 from the right, we go to infinity, right? And over here, as x goes to negative infinity, we again go to 0. But as x approaches 0 from the left, we head down to negative infinity. So no max, no min. All right, moving on. Next graph, square root graph. To get a real number here, the lowest I can go for x is 0. Right, as soon as we go to a negative value, we no longer have a real number. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3, so on and so forth. So graph looks something like that. This is interesting in that our domain, right, if we want real numbers, our domain is from 0 to infinity. 0 is included. Our range, also from 0 to infinity. 0 being included again. We do, of course, have a 0. It's right there, the origin, 0, 0. We don't have any asymptotes there. In behavior, as x goes to infinity, the function goes to infinity. Notice x cannot go towards negative infinity. We would say as x goes towards 0, the function goes to 0. Intervals of increase, decrease, we're increasing from 0 to infinity, and no interval of decrease. All right, moving on. Our cube root function. Cube root function, it's nice to start right there at the origin, right? Cube root of 0, 0. Cube root of 1 is 1. Cube root of negative 1 is negative 1. Then I got to go all the way to 8 to get another clean, nice point, right? Cube root of 8 is 2. Cube root of negative 8 is negative 2. So we get a graph that looks something like that. Okay. So our domain is all reals. Our range, all reals. We do have a 0, right, at the origin. X. Okay. No asymptotes, no max, no min. In behavior, as x goes to infinity, the function goes to infinity. As x goes to negative infinity, the function goes to negative infinity. And notice we are always increasing, right? So we're increasing for all real numbers. All right, moving on. Here's Unit 5 stuff. Parent graph for sine. So remember, sine would start there at the origin. And it's going to, with a positive a value, right? We're going up. We go down, and so on. So on. So there's our sine graph. Remember, our max right there is 1. Our min right there is negative 1. So domain, all reals. Range, we're bounded from negative 1 to 1, inclusive. Zeros. We got lots of them, right? We've got a 0 right there at the origin. Our next 0 would occur right there at pi, and then we'd have another one at 2 pi, negative pi, so on and so forth. So our zeros are pi n, or pi z. I like z for integer, right, where z is an integer. And no asymptotes. And of course, plenty of max and mins. Okay, moving on to cosine. Of course, very similar to sine, right? But instead of starting at the origin, we start at our maximum. And from that, okay, so there's our sine. Again, same domain, same range. The only difference is our zeros now. Our zeros occur at pi over 2, and then every pi units from that. So our zeros here, pi over 2 plus pi z, again where z is an integer. No asymptotes, right? And again, we have max and mins, but they're all, of course, shifted by pi over 2 from where they were with sine. All right, moving on to tangent. Tangent does have vertical asymptotes, right? At pi over 2 and at negative pi over 2. Tangent goes through the origin. Okay, looks something like that. So on and so forth. Okay, so our domain, this is where a lot of us made mistakes on the Unit 5 test, right? We had trouble finding the domain when we had asymptotes. Well, our domain is everything except for those vertical asymptotes, right? So all real numbers except pi over 2. And then how far do I have to go to find the next one? Oh, I have to go pi units in either direction. So all reals except pi over 2 plus pi, or z pi, or pi z. Again, where z is an integer. Okay, range, all real numbers, right? Zeros, well, we're going to have plenty of zeros, right? Here, pi, so on and so forth. So our zeros are at pi z, where z is an integer. And of course, asymptotes, we already kind of mentioned those when we talked about our domain, right? Our asymptotes are at pi over 2 plus pi z. Okay, on to our next page. All right, we have cosecant. Remember, cosecant is, of course, 1 over sine. So you might start by graphing sine. So I'll graph sine in a different color. And again, sine goes through the origin. Okay, so something like that. It's 1, that's negative 1. Okay, now we get an undefined value anywhere we do 1 divided by 0. So anywhere sine hits 0, right, we have a vertical asymptote. Okay, and then to draw our graph, remember the reciprocal of 1 is 1. The reciprocal of negative 1 is negative 1. And then as we move away from those points, we either head to positive infinity or we head down to negative infinity, depending which side of the graph we're on. All right, so our domain, all reals except wherever we have these vertical asymptotes. In this case, this is at pi, right? So negative pi over there. So all reals except pi z. Range, We go from negative infinity to negative 1. Negative 1's included. Union 1 to infinity. And 1 is included, so that should be a bracket. Okay, there's our domain and range. And of course, we have plenty of mins and maxes. All right, moving on to secant. Secant is, of course, 1 over cosine, so I would recommend go ahead and graph cosine. That's 1. Down here is negative 1. Okay, and anywhere we hit 0 for cosine, the reciprocal will be undefined, creating a vertical asymptote. And then go ahead and sketch in your secant graph. All right, so now my domain would be all reals except this is at pi over 2, right? And this is negative pi over 2. So domain, all reals except pi over 2, and then I have to go pi units to get to the next asymptote. So all reals except pi over 2 plus pi z, where z is an integer. Oh, and on the last one I forgot to mention, notice there's no zeros here. Okay, and you can see range is going to be the same for secant as it was for cosecant. Okay, moving on. Cotangent. Oh, strange, we kind of jumped back there. We did tangent already, but cotangent, you're going to have asymptotes, vertical asymptotes at 0, at pi, negative pi, so on and so forth. And we're going to have zeros at pi over 2, negative pi over 2, so on and so forth. Okay, so our domain, all reals, except wherever we hit these asymptotes, right? 0, pi, negative pi, etc. So all reals except pi z, where z is an integer. Okay. Range, all reals. Our zeros, pi over 2, right? And then how far do I have to go? Pi units, so plus pi z. That'll get us to our zeros. Okay. And of course, asymptotes, I already have them right there, right? Pi z. Okay, on to our last parent. We're doing a log graph here, and we go with log base 2 as the simplest log graph. Okay, so when we go ahead and graph this, remember this is the inverse of an exponential. So we're going to be having a vertical asymptote right here. Right? Remember, exponential has a horizontal asymptote on the x-axis, so our log has a vertical asymptote on the y-axis. All right, since it's base 2, let's see, we'll have points like 2 cubed is 8, so that point would appear right there. Okay, 2 squared is 4, so that point would appear right there. Okay, 2 to the first is 2, so that's right there. Okay, 2 to the 0 is 1, so right there, so on and so forth. So there's our graph for our basic log function. All right, domain. Notice I can't actually put 0 in, so it's an open boundary, 0 to infinity. Range, all reals, right? We go down forever, we go up forever with no breaks. We do have a 0. Our 0 is right there at x equals 1. And we do have a vertical asymptote at x equals 0. In behavior, as x goes to infinity, the function goes to infinity. As x approaches 0 from the right, the function goes to negative infinity. Okay, so hopefully that's a good review. Now go ahead and pause the video and take a look at the next section. We're going to go over various scenarios, or in other words, word problems, and we're going to try to figure out which of all of these fun equations we've covered would match it. So go ahead and pause it and give it a shot. Okay, so hopefully you gave these a try. Let's go ahead and go over them. So looking at our first scenario, we're talking about the length of time that it takes a pendulum. So remember, a pendulum is something that kind of swings back and forth, right? Back and forth. More like this way, right? On a clock, right? So it's swinging back and forth. And it's saying we have a square root function with a proportionality of 0.32. So that tells me 0.32 times the square root of the length. I'm just going to use x because if you look forward, right, our choices are all using x as our variable. Okay, so there's that one. All right, question 2. This time we're talking about a step function, right? So we have a step function, and each case comes with 12 cupcakes. So x over 12, right? And we have to round that way because, right, if I have, it's okay to have extra cupcakes, but we don't want to be short cupcakes, so we have to round to a ceiling. All right, question number 3. Okay, here we're talking about the volume of a rectangular building, or in other words, a rectangular prism. Volume is, of course, length times width times height for a rectangle. So 5 feet longer, 10 feet taller, we have this relationship where we have one length, we have another one that's 5 feet longer, we have another one that's 10 feet. So there we go, looks like a nice polynomial. All right, number 4. Anytime you see something about a projectile being launched, something thrown, kicked, hit into the air, we know it's quadratic, right? It's going to be a parabola. So we just have to pick out the values to fill into our quadratic equation. So here we're going to have, right, constant of gravity, 9.8. And then let's see, 19.5. Starting or initial height of 58.8. So there's number 4, quadratic equation there. Okay, number 5. Sound wave. So that tells me sine or cosine right there. Okay, and we have a height or amplitude of 4. So A is 4. Talking about sine. And 440 hertz, that tells me 880 pi x. Okay. All right, moving on to our next page. Okay, Here we're talking about real estate, and real estate, of course, and anything to do with loans, right? We're seeing interest either being gained or lost, right? Depending on your perspective. In this case, compounding continuously. So that's our PERT formula, right? So this one is initial amount times E, and our rate was 0.05 to the X, where X would be our time in years. Okay, next one's pretty long. Reading through that, you got a lot of numbers going on there. Some of the key words: proportional to the square of the distances between them. Okay, so that tells me my denominator is going to be the square of the distance between them. So x squared is my denominator. Okay, and then my numerator is, of course, the product of all of that fun stuff. So 6.6 blah 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 times the 5.98 blah 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 times the 2.2 blah blah blah. So there's number 7, rational function. Okay, number 8. Again, you're seeing these words proportional a lot. Okay, and I'm seeing the word, keyword there, cube root. So this is a cube root function. So we're looking at the 62.1 cube root of my variable with an initial or starting height of 76 centimeters. So cube root function there. Okay, number 9, this is something we talked about briefly in 6.1. If this car is coming at us at a constant speed and then it passes, right? We know that this is an absolute value function, right? So let's see, 20 yards is a key value there. And it takes 3 seconds to be even with us, meaning the vertex, right, would be at 320. I'm sorry, the vertex would be at 3. Okay, moving on. This one, I wouldn't expect you to know unless you're in chemistry or AP chemistry. So that one I would, if it were me and I had the multiple choice down here, I would go skip it and come back. But anyway, if you are in chemistry, you know that this is a logarithmic scale. So it's going to be negative log of x. Okay, and our last function here. So $6 per game plus an initial $4 shoe rental. Keep in mind the domain here, x, has to be a whole number only. You can't play negative number of games and ask them to pay you. You also can't play fractional games and think you're getting a discount. So this is really a step function with the domain of x being greater than or equal to 0. But you could use this as a linear and just say domain x must be a whole number. Okay, so you can now go back and find all of these equations here in our equation bank. Okay, so moving on to our last page. Graphing these. So which one was linear? Well, that was the very last scenario, scenario 11. My model was 6x plus 4, right? So that gives me a y-intercept of 4 and a slope of 6. Okay, but again, in real life situations, x would have to take on only whole number values. So this linear equation really isn't quite appropriate because we do have all these fractional values as well as negative values that don't make sense in context of that scenario. So please limit that domain to whole numbers. Okay, next, the exponential. Looking back, that was question number 6, scenario 6. Our model was 821,500 e to the 0.05x. Okay, so at time 0, right, that would be 1, and we would just have 821,500. So there is our intercept, our y-intercept. Okay, and we're going to have a graph, whoops, that looks something like that. Okay, next, our quadratic. Looking back, that was scenario number 4. Our model there was -1/2 times 9.8 meters per second squared, 19.5x plus 58.8. Okay, so 58.8, that tells me, hey, there's my y-intercept, right? Okay. And graphing this guy, we're going to go up through that y-intercept. All right, we're going to hit a maximum height and then head on back down. If you want to find that maximum height, right, find the vertex. You can use the negative b over 2a, or you could complete the square to find the vertex. Okay, next we have absolute value. That was scenario number 9. Our model was 20 times the absolute value of the quantity x minus 3. Okay. So it tells me my vertex would be over here at 3. Our slope is quite steep, 20. Okay. And that means when x is 0, that would be 60. So there's my y-intercept. All right. Next, our step function. This is scenario 2. Again, you could say it's also scenario 11, really. And our model for scenario 2, x over 12. So when x is 0, we're technically at 0. Right? We don't need to buy any cupcakes if no one comes. But as soon as we go past 0 guests, right? As soon as we hit 1 guest, we would jump all the way up here to 12. Right? And then we would hang out there. And then we would jump again. I guess I could use a little smaller scale there. Okay. And again, in context of the problem, it wouldn't make sense for x to go negative. So our domain in context of the problem would be whole numbers for x. We can't have fractional people coming either. All right, next, our polynomial graph. That was scenario number 3. And our model, x times quantity x plus 5 times quantity x plus 10. So we have zeros at 0, at -5, and at -10. They're all multiplicity of 1. A is positive, and this is a 3rd degree polynomial. So odd degree, the end behavior, right? One end goes one direction, the other end will go the other direction. Since A is positive, we're going to go up on the right. And we're going to go down on the left. So something like that. Okay, our rational, that one was scenario 7, and that was the really big 6 point, was it 6 point something? Yeah, I don't want to write it. It's this one right here. Okay, and Graphing that, these values are just not pleasant to graph, ladies and gentlemen. I really don't want to graph that by hand. Go ahead and plug it into Desmos and take a look at what the graph looks like. Okay, I'm going to move on. Next, the square root. This one was scenario number 1, and it was 0.32 square root of x. Square root function, our a value is pretty small there, right? So when x is 1, we're at 0.32. When x is 4, we would be at 0.64, right? So we got to go pretty far just in order to get x to be, our y value just to make it to 1. So it's really, really flat. Okay, something like that. All right, our cube root scenario, that one was number 8, and it was 62.1, the cube root of x plus 76. Okay, well that's nice. I know my y-intercept is 76. Call that 76. And it's a cube root function, so we're going like this. And if you want to find the 0, you can go ahead and solve for that 0 if you really cared, right? It would be negative 76 divided by 62.1 cube rooted. Okay, our logarithmic scenario, that was scenario number 10. And our function was negative log of x. Okay, so that's simply our common log base 10, but we have a reflection on it. So we're going to come like this. Oop, I went too far down. Sorry about that. Got a little bit excited. So something more like that. Okay, ignore this part. Okay, on to our sine, cosine, secant, cosecant model. This was scenario number 5. The model was 4 sine 880 pi x. Okay. So graphing that, our max is 4, our min's negative 4. Okay. I'm going to go through the origin, and we're going to go up and down, and so on and so forth. Okay. And of course, this right here would be at 440. Oh, I'm sorry, not that one. Be over here, 440. Right, 1 period, 440. Half a period, this would be 220. Okay, and I don't think we had a tangent cotangent model in this mix. Nope, don't have one. All right, so that's the end of the lesson. Hopefully that helps. Go ahead and watch Mr. P's version as well, and good luck on your homework. Thanks a lot.